Hi everyone, am I audible? Can someone respond by unmuting? Hello?
Yes, sir.
Yeah, okay. Yeah. So, yeah, it's time, so we'll start our session. So, I'm Lalit, and we'll be discussing questions based on week 5 lectures. So, before we start, I will just share the screen. Yeah, yeah. Hope my screen is visible. So, let's start. So, what were the topics discussed in week 5? Anyone just unmute and start. Just, I mean, we'll just go through a few, I mean, brief overview of the lectures and then we'll go for the questions. Anyone? So the week 5 started with what topic? Yeah, you can. Yeah, no? Week 5. I'm saying. Today's discussion is based on week 5, so we'll just focus on that. Week 5 started with uh, wavelets, right? With a revision of wavelets, which was done in week 4.
Har
So,
wavelength.
yeah, specifically Haar wavelet, but yeah. So there was bit of revision going on there. What was wavelets and then what Haar wavelet meant there. And so what is wavelet? Anyone? Anyone? I mean, this was also done in week 4, so should be kind of easy. Why do we need wavelets?
For compression purpose.
Uh, okay, that's fine, but why exactly? I mean, what was the motivation that was given in the lectures? Compression is an application, which is fine, but there was a more critical issue uh, that was prevalent out there. So that's why wavelet was proposed, wavelet transform. So why wavelet transform? Um, Anyone remembers time, frequency, uncertainty? It was discussed, right? What is that time, frequency, uncertainty? So if you try to analyze things in time, you may not be able to precisely tell the frequency. But if you try to analyze things in frequency, you may not be able to say what at what exact time did that frequency occur. So with Fourier transform, it was clearly been seen that we don't have that time information out there. We are just able to get frequency of the full signal. But for instance, if the signal is non-stationary, meaning the signal's frequency keeps on changing over time, then you cannot say at which time instant what frequency was present. So keeping all these things in mind, wavelet transform I proposed, which used wavelets. So each of these wavelets, or what it was called in class as mother wavelets, were containing, I mean, they had a few properties that you can vary their frequency. That means the variation of each of these wavelets functions, and they are of limited duration in time. And the average value of these wavelets is always zero. So given these properties, you can, given any set of functions which have these properties, you can use wavelet transform like that. Maybe you can apply wavelet transform. And yes, wavelet transforms then now, I mean, is now able to capture better because you can vary both frequency and you can also translate it. So you can, with that translation part, you can exactly say at what time, what frequency content was present. And if you want to analyze frequency at a given time, you just vary the scale factor out there. So the scale will be inverse of the frequency. Okay. So with this, I mean, this was there, wavelet transforms. And then what else? Uh, some multi-resolution. Yeah. So the signal was actually decomposed into multiple resolutions so that the signal can be analyzed in those specific resolutions. Why do we need this multiple resolution concept? Why can't we just analyze things on a single resolution? Anyone? Why did we need this multi-resolution analysis? So can I mean anyone can just give a small example, right? I'm not expecting any concrete result out there. Anyone? If you remember, there are different size of object sizes out there. If you take an image and the object sizes are different, then what kind of resolution you need for big objects to capture big objects? Hmm? You need you don't you I mean you can of course go with high resolution, but even with low resolution you can actually capture that object, right? But if you have a very small object, then and you want to try to detect that object, for instance, then you need a high resolution uh, image. You cannot deal just with a low resolution image because if you have low resolution image, the object may not be captured properly, small object. And even the same thing with the contrast. If the contrast is high, it's easy to analyze that specific scene. But if the contrast is low, then the problem is everything looks similar. So you might want to actually go through each different levels of resolution to understand how the contrast is changing. Is this fine? So after the specific discussion on multi-resolution analysis, there were filter banks that were discussed. One was the quadrature filter, where if you specify just a low pass filter, you can actually specify the high pass filter, and even so, this is at the analysis side. So, what does analysis do? You want to decompose the input signal or even the image into different components, the low frequency component and the high frequency component. And then at the synthesis size, you want to collect all those individual components like low or high frequency components, and then you want to add them to get the original image. So that's the synthesis part. Okay. So given this, there was quadrature filter defined, and then there was also orthonormal filters which are defined. Given the and after that, what was there? 2D Haar wavelet transform. Does anyone remember this? What does it mean? 2D Haar wavelet transform. So the wavelet transform, I mean, whatever the definition was given earlier, that was only applicable for one dimensions, but the images are in two dimensions, right? So given that we have two-dimensional signal, we need to have the transformation now in two dimensions. So how to do that? So one was the standard way where you actually apply the wavelets in a row and then rearrange the rows in such a way that the uh, averaged part is one side and then the informative part is the differences and the average part is the sum part, right? So the sum part and the difference part have been, or the difference part or the detail part as given in the lectures. The detail part is kept on the other side. You rearrange it and then you apply the same thing over column and then rearrange it. So this gives a 2D wavelet transform, well, specifically Haar wavelet transform. But there is another method called non-standard method where you decompose again in each row and then decompose in each column and then repeat the process on the quadrant containing the average direction. So if you decompose it in each row and in each column, so you will find that the upper left quadrant has the low frequency part, and then you can continue doing the process on that upper left quadrant, the process of decomposition. So that is the non-standard way of doing the wavelet transform. So given that we moved on to the next lecture, what was it? Anyone? What's the next topic? What that was taught in the lecture after wavelet transforms?
Image enhancement.
Yeah, image enhancement. So in general, image transforms were there. So what kind of image enhancement techniques were discussed? Mostly the spatial ones were discussed. So what kind of image trans enhancements technique you can do? The first is what? Point operations. What is point operation?
On pixel data, we
Um, on pixel data, yes, that's true. Anything more?
like contrast stretching.
Oh, no, I don't want example. What do you mean by that? Yeah, that's an example. That's fine. But
Yeah.
what's the meaning of point operator?
Transform the value of pixel, which will give transformed image.
Okay, so that transformation is pointwise, meaning given an input pixel, you just transform it based only on that single input pixel. So that is point operator,
Yes.
and it will not depend on any other pixels. Only that specific pixel value, it will the transformation will depend. I mean, the transformation will take input only the specific pixel value and not any other value. The next one is spatial operators. What does it do? Spatial operators. So as the name says, it's not a point now, it's a space. Any idea? So now you don't consider a single point, but a space around that point, which is called as window. So if you consider a window around a point and then try manipulating the central pixel based on the values of the nearby pixels, then you call it as spatial operators. Okay. The next is frequency domain operators. What do you mean by that?
To convert the image into frequency spectrum and
Hmm.
apply enhancement techniques on that.
Yes, I mean any techniques actually.
Yes.
Since you're discussing image enhancement, so it's fine. So, for instance, if your image is noisy, I'm just giving an example, and that might have been discussed in further lectures. But so, if your image is noisy, what do you expect in frequency domain? Your frequency, or how do you think frequencies will be? Frequencies, I mean, there will always be a low frequency component, but you will also have too much of high frequency component, right?
Yes.
Because the image is noisy. So when your image is noisy, you will have maybe I'll just use this. If your image is smooth, you will have some smooth structures out there. But when you have noisy uh, image, there will be some sort of, I mean, these dots or some other kind of things that reveal that this has high frequency component, right? So when this has high frequency component, what is it that you expect? That you'll in the frequency domain you can see the magnitude high for the high frequency parts. Well, anyways, for the low frequency part, it's always there, but even for the high frequency parts, you see the magnitudes are high. So what do you want to do? I mean, as a simple solution, you can just try to cut off those frequencies which are high enough so that the specific dots can be removed. So that's something you can think of it as frequency domain operations. And the fourth one is pseudo coloring. So pseudo coloring is also, I mean, it comes under image enhancement. So if you see 70, 80 years old films, you can clearly, so they were shot mostly in, well, not mostly, they were all of them were shot in black and white, right? But now since we have so many other color televisions with such high quality, we would like to see them in image with color to have a better perception of what that picture is portraying, picture or even the film. So generally, there are there are a few companies out there who actually take the old black and white films and try to convert it to a color image. So that's called a pseudo coloring because that's not the actual color, but that's what we expect that color to be. So it's a pseudo color. Okay. So given this, yeah, someone said about contrast stretching. Contrast stretching is one of the what point operators. So any other point operators that was discussed in class? Point operators. One is contrast stretching. What is contrast?
Thresholding.
Yeah, sorry. Yeah, thresholding. Yeah, contrast stretching. What does contrast stretching do? So if your image
From
contrast, yeah, yes. Sorry, continue.
it will transform one histogram to another histogram. Uh,
Yes, but
and
what's the aim?
aim is to get the uniform PDF
Okay,
across
yes,
all the.
yes, yes. So I'll just simplify those words. I'm not using those specific technical words. So contrast stretching means if your these are the image values, intensity values are, and this is what the count of those specific intensity values. So if you have some image which has contrast like this, you might want this specific range to be increased such that it covers the whole of the input whole of the pixel intensity space. So that means you want something of this sort. May not exactly be uniform, but it is close to uniform. So you are actually trying. So now the minimum and maximum values are also stretched. So this is what contrast stretching means. And then someone said thresholding. What is thresholding? Anyone?
It is a cutoff intensity value below which
Yeah.
the image will
So
be
yeah, it is a
negative.
cutoff intensity value below which we map everything to zero, and here we map it to maximum value, which is L minus one, above which we map it to L minus one. Yeah, that's it. So why do we need thresholding? Any guesses? Or any simple example? I'm not a- So all these are derived because we want to see images properly, and that has nothing specific to do with mathematics. We develop these techniques so that our image perception improves. That's what the aim is. Aim is about image enhancement. Yeah. So why thresholding? Why do you need thresholding?
For black and white image, converting the image into black and white.
Uh, okay. Anything else?
Actually, understanding is depends upon the thresholding graph. The output is varying transform
Yeah, that's
because of the
fine.
transform.
No,
Yeah.
I'm just
So
asking where do you want to use it?
for
In segmentation,
gamma correction for display.
Gamma correction. Okay. You don't really use thresholding for gamma correction.
for segmentation,
Yeah. So the best way is, I mean, that's the classical thing to do. If you have a threshold, then you can segment images into different parts, maybe foreground and background. If your foreground is dark and background is bright, then you can have such thresholds so that you can clearly cut off foreground or background. Or the some other nice example given in the lecture where in some medical images you just want to focus on some specific areas to understand whether some specific tissue is affected by disease or not. So for focusing on the specific part, you might want to just remove other parts of the image. So that can be done. One of the ways is using thresholding. Okay. So one specific transform which I thought I should discuss is this S. I mean, all these transformations can be written as S equals to TR, where T is some transform. R is in the original space, original pixel space. S is in the new pixel space, pixel intensity space. Okay, given this, so there was one of this given as S equals to C log mod R plus 1. Can anyone tell why mod R? Why do we need mod R?
Uh, mm, Mod usually negative become positive.
Yeah, so that means,
That means we will not get a zero. Suppose R is minus 1 means minus 1 plus 1 becomes 0. So log may go to infinity, log of 0.
okay.
So to avoid that, we are taking mod.
Yes, so I hope everyone knows that the domain of log is what? What is the domain of log? What is the
Mi-
valid input value?
Minus infinity to plus infinity.
No,
So
domain starts from 0 to infinity.
0 to yeah, yes.
So if your domain, I mean, if you want to do any kind of transform, so any transform should actually uh, should make sure that should be within the domain in the sense that input to any transform, yeah, input to any transform should be within the domain. So if we have anything within the domain, then only we can will be able to map it to a new value. Okay, so given this specific idea, how does the log graph look like? What is the base for log?
to the base 10.
Take any base actually. What base? What are the valued values of base?
E actually.
Say 20.
Sorry, someone said E. Okay, and the other answer?
E base is E.
No, base is E. Okay. No, anyone any other values that we can take?
Base 10 can be used. Base 2 is used. Uh, Depends upon the application that is base is selected.
Okay. So what are the valued values for B in general as a maths person?
Base value. Decimal you are talking 10 base 10.
Base.
Yeah,
What is
base
the
10 decimal. We are using base 10.
no. What are the valued values of B, that the base can take?
Okay. For the log E 10 and 2 are used.
It is 1 to 10. B.
Okay. You are asking range or
No, B. I
B
wrote right
could
base.
be 1 to 10.
No. So okay, is one useful enough? Can you take base as one?
base 1?
Base one
No,
is equal to
no,
no.
no, no.
No, right? Why?
Yeah, because the
Log one is zero.
logarithmic, no, actually the logarithmic purpose is suppose if with the huge number we can make it as a small.
Hmm.
Suppose 1000 means 10 power 3, then it become 3 if you take log 10. So the bucket size, range size you can reduce actually.
Range size we can reduce.
Log one to the
That's
base
fine.
one is invalid. Log one to
That's
the base one is invalid. That's why we have not taken the base
yes,
as one.
yes. That's the answer. So if everyone can see this specific equation y equals to log x to the base b, this can be equivalently written as b to the power y is x, right? Everyone agrees
Yeah,
with this.
yeah.
So if I give you some input x, but then I give you a base 1, what does it mean? Base 1 to the power something is always 1, right? You can
Yeah,
never
yeah,
define the log. So it's
yeah.
not defined. So yeah, in
It,
short, yeah, yes.
it is equal to same value.
Yeah, 1
Base
to the
value
power
1.
something is 1. You cannot have any specific x out there. It's always a constant. So b can actually be between 0 to 1 and then b can be greater than 1. That's all the range. So when b is greater than 1, that's when where you can use this image transformation out there properties, right? If I just go with this specific notation, it's x and this is y. This is for b greater than 1. And if b is less than 1, it will turn out to be like this. This is at 1. Okay. So this is a small technicality that everyone should know, that you always consider this case where b is greater than 1. At least when doing implementations, we should make sure that the base is greater than. Okay, so given this, okay, fine. This was just a short note on this log transform. And then what else? Someone said gamma transform. Yes. What is gamma transform? Gamma transform will look something like y equals to c into x to the power gamma. Right. So where gamma is some power that you would like to erase the input. So yeah, why is it useful? Because in the old TVs like CRTs and all, there was a gamma distortion out there. So if you give a linear input, the output will be gamma distorted. So you want to manipulate the input in such a way that their output is linear. And that's the main motivation why gamma transform came into picture. And then there was bit plane slicing that we'll be discussing soon enough with the question. Then just seeing the histograms. Yeah, histogram equalization was also taught in the class, and after that, histogram specification. So, given a specific target distribution, how would you like to deal the how would you like to convert the current image into the target distribution? Okay, and then the last lecture goes with image filtering, where what kind of filters did you use? What kind of filters was taught in the class? It was mostly spatial filters.
Yeah, spatial average.
Yeah, I mean spatial filters. There was average, there was difference, all sorts of filters. So mostly spatial filters were given, but in that specific cases, you have average filter, Gaussian filters, and then which are low pass, and then edge filters, which are high pass, and then you actually try to use other sorts of non-linear filters like median, min, max filters based on the kind of noise that you have, right? So when would you like to use average filter?
To to reduce high frequency noise or to
No,
soothe the
that's okay. That is quite a general statement. Anything specific?
smoothing the image, blurring
Oh,
actually.
blurring is fine. I mean, but okay, in the context of filtering, why would you like to use? When you have noise, right? What kind
Yes.
of noise do you generally assume for the average?
Mm.
Zero mean Gaussian noise, right?
Okay.
So you zero mean Gaussian noise, and the standard deviation is same for all the pixels. So under that condition, when you actually average out over a set of pixels, you can see that your average value is very close to the ground truth value. Ground truth means the original image with a non-noisy image. So under that assumption, you use average filter. Again, now someone said, yeah, you can use Gaussian filter as Gaussian weights instead of just taking uniform weights over the filters. That is called as Gaussian filters. And if you want to detect edges, then you can take, I mean, you can just remove the identity with the low pass filter, you get a high pass filter. Why is it high pass filter?
It allows high frequency,
Yeah,
which
but
is equal to edges in the image.
yeah, yes. So edges actually denote the high frequency component of the image. Since they are they denote the transition between one pixel to other pixel. So those transitions are the measure of frequencies. Okay. So given this, yeah, there was median, min, max filter. When do you use median filter?
Salt and pepper noise.
Okay. Yeah, for filters, what we did is average filter, which is mostly for Gaussian noise. And the second one is Gaussian noise with zero mean and fixed variance for all the pixels. Again, Gaussian filter, you can also use it. And the third one was edge detection, which is high pass filter. And the last one that we checked now is median filter. Yeah, someone said salt and pepper noise. What is salt and pepper noise?
Median filter.
No, no. What is salt and pepper noise? Someone said median. I mean,
It's
you
a
see,
dot.
The,
yeah,
It's a dot.
the,
Dot. The abrupt change in a small portion.
yeah. So your pixels changes abruptly in the sense that
mm.
either they suddenly go to 0 or 255. Then they are, I mean, going to 255 is the salt part, and going to 0 is upper part. Well, 255 here means number of levels minus 1, not exactly 2. Whatever your intensity range is, 2 to the power L. So based on that, you have, okay, so L is 2 to the power K rather. If it's an 8-bit image, then it's 256 minus 1. Okay, so given this brief idea, and then the last topic that was done is bilateral filter. What is bilateral filter? Why bilateral? What is bi in that? What are the two things out there?
It reduces the noise, at the same time it preserves the edges. It's,
Yes, that's the property, but what does it do?
It considers geometric closeness as well as photometric similarities.
Okay. So what about other filters? What does these filters consider?
Only geometric closeness.
Are you sure? So these filters consider only the photometric similarity. They do not take pixel location as the input, right?
Yes, yes, correct.
So pixel locations, so yeah, the all these filters take intensity values as input, which is what your photometric uh, photometric signal rather, or information. Signal is still not technically right. So this is the photometric information that you use. In this specific case, it is photometric information, as someone said, plus geometric information. What is geometric information out there? So the geometric information here is closeness of the pixel intensity. Sorry, pixel locations. Yeah, that is the geometric part of it. Okay, so of course we'll discuss these things in more details as soon as we arrive at those specific questions. And today's questions are actually kind of simple because they don't really have too much mathematics out there. So I thought of just going through the lecture in a bit more detail. Okay, so we'll start with the first question for the session. Any doubts till now? Okay, that's good then if there are no doubts. So we'll start with the first question, that given an image patch like this, two numbers, after the gamma correction, the value of the central pixel will be dash. Okay, so what is the equation for gamma correction?
S equal to
S is
uh, pixel
I
it's
put it
value power
here,
gamma.
which is
R
C
E
into
R
R to the
into
power
R.
gamma,
The power one
right?
upon. Mm.
R is the pixel value, C is some constant, gamma is what? Your gamma value, what your gamma correction you want to do. Okay, S is in the transformed, S is the transformed intensity value. So again, this gamma correction does not take into account any geometric information, it just takes what? What does it take?
Intensity.
Yeah, intensity or the photometric information. And what kind of operation it is?
it- power
Scaling
mo-
operation.
increasing, monotonically increasing function. It's a
It
power
depends
function.
on gamma. That's fine. But
Mm.
what kind
Mm.
of operation is it? Does it
Stretch
I.
is it point operation or is it spatial operation?
It's a
spatial.
point operation.
It
No,
is
point
point
operation.
Point
operation.
Sorry, point
operation.
operation. Correct, point
Why?
operation. It's
It
state
works
only one
on
Point.
point.
Pixel
individual
value.
pixel.
Yeah, so it's a point operation. So yeah, if one knows this formula, of course everyone can solve it. That's fine, but you should actually try to take into account what's actually happening. Okay, so first we'll get this uh, C value. The constant value is given by I'll just call this value as P. Since we are concerned with the central pixel, we'll take the central pixel as
65.
P. P upon maximum value, which is L minus 1. This is how the constant is related. Okay, I'm sorry about that. Okay, so R is not the pixel value here. That's my misunderstanding. Sorry about that. So C is equals to L minus 1 and R is equals to P upon L minus 1. So what we try to do is we want to scale it to the maximum level. That's why we take constant as L minus 1. But then we want to correct it only relative to the maximum value and not the exact specific value of the pixel. So when we correct it relative to the maximum value, then we have to divide it by the maximum value, right? Okay. So now, if you take L as 255, which is the general image, the value of R is what?
65.
Yeah, P is 65, and what about, yeah, this is 65 upon 255. So your S will be 255 into 65 upon 255 all to the power, the gamma value is 1.25. So if you solve it, it turns out to be 85. That's the answer. Okay, so I hope the question is clear. Yeah, I just made a mistake initially that this is a function of P. It is again a point operator. There is no problem with that. But then this specific R is not the grayscale value, but it's the relative value with respect to the highest permissible value. Okay. Okay, then we move on to the next question. Next question is about histogram equalization. Why do we need histogram equalization? I know I'm repeating that question, but still good to general ones. Yeah, why do we need histogram equalization? What's the aim of that?
To get a better picture actually.
Okay, but anything more? Technically speaking, of course, that's perceptual, which is fine. But
Balancing the pixel values or the intensity and contrast.
It's a
we want to
contrast.
increase the contrast, yes.
Yeah, contrast.
Contrast.
Yeah, so the whole idea is, as someone said, that we want to make your histogram in such, transform the histogram in such a way that it looks nearly uniform. That's the whole idea. So if this is your histogram, it should almost be uniform. That's the main idea of histogram equalization. So for the specific method, it's if someone remembers SK is what? It's a 3-bit image. SK is the transformed pixel value, and which is again I'll write it as T of RK, which is what? L minus 1 into summation over J equals to 0 to K Nj upon capital N.
Capital N. Yeah.
What is Nj? What is N?
N is number of pixels, small n.
I've written capital N, which is total number of pixels.
Total number of pixels.
Number of pixels, and small n is
So,
pixels
The
per intensity, right? Intensity value for jth intensity value. Yes, this table means that, right? That for intensity 1 there are 1023 pixels, intensity 3 there are 656 pixels, things like that. Yes. Okay, so what is this ultimately doing? How does this look? Of course, now it's a
yeah,
simple formula. If I can apply, it's fine. I can get answer. But what does it mean?
it is equalizing the probability of each pixel.
Oh, which is okay. That is fine. I mean, that's the aim. But anything else?
Actually,
Have
the
you seen?
summation of j equal to 0 to k is a CDF formula. Correct?
Yeah, yes. This is the cumulative distribution.
Yeah.
So CDF, as people generally say, CD, but yeah, CDF of this intensity values. So it's a discrete if you consider, uh, yeah, if you consider this intensity values as discrete random. Sorry, if you consider intensity values as your space in which you are assigning probabilities, that is the probability. It's a part of probability space, and then if nk is the nk is the pixels per intensity value. So if they are the particular probability masses, that means number of times these occur. If I mean you generally say it that way, then this can be thought of as a discrete probability distribution, right? Discrete probability distribution. So discrete probability distribution where your random variable is what? Rk. Rk is a random variable, and this nk is the discrete probability distribution for that random variable Rk. Yes. Does everyone agree with this?
yes.
Yeah. So that's it's a nice interpretation, and that's how people have come up with histogram equalization. So given, I mean, this formula comes because you want to use the cumulative distribution of the probability distribution of this probability of this probabilistic setting, given that you take this R case as random variables. Okay, fine. So of course now this is just an interpretation. We'll just solve the question. So I'll just rewrite the table, but with somewhat more information. R varies from 0 to 7 since it's a 3-bit image, and these are the specific values. What do we need to do? It is this value is the discrete probability distribution nk upon n and not the nk itself. Okay. So we need to find this discrete probability distribution. If someone just divides it by the total number, it turns out to be something like 0.19 and then
0.24,
0.25. I mean, I'm just
0.20.
almost similar. I mean, I'm just rounding it off.
Yeah. 0.0506, 0.03,
Yeah,
0.02.
just copying numbers from whatever I solved earlier. Okay, so given this, what is so we now have nk upon n. What is it that need to be done? So now if I take S0, what it will be? L minus 1 again. L is what? L is 8.
L is 8.
Yeah, so your L minus 1 will be 7. 7 into summation over here we don't have any summation. J equals to 0 to 0 actually. Then what is this? Nk upon n is point. I just write it. Yeah, 7 into 0.19. So whatever the value is. So for S1 it is summation over j equals to 0 to 1 nk upon n, which is 7 times 0.19 plus this is 0.25. So whatever these values turn out to be. So this will, okay, I'll give you one example. This is 1.33, this is 3.08. Can you just leave it here like this? Is this correct?
Yes.
We have to round off to make it
Yeah.
our quantized value.
Yes, yes. So the problem with us is that we live in a computer world, so we have to quantize it. And given that we have a 3-bit image and it always takes integers, we have to round it off. Okay. So now rounding this 1.33 will give you 1.
1,
3.08 will
3.
give you 3. Okay. Things like that. So you can take up to S7. Okay. Is this question clear? Okay. We'll move on to the next one then. So, yeah, again a simple question, I guess. So you're given a noisy patch like this. Use median filter to determine the denoise central pixel. Okay, again I'll repeat the same question. Why, when do you use median filter?
Salt and pepper noise.
Yeah, salt and pepper noise. Okay. So what is the basic intuition out there for median filter?
Because it won't take lowest value or highest value. Because it's
Yes.
taking a median value, so
Median.
it will neglect salt and pepper values, which is 255 and 0.
Okay. Okay. So I'll give two examples. The first is a first is what do you say, some image patch which looks like this, and the other is noisy version. Okay, so I assume that it just has three values. The noise here is like instead of 1 it goes to 0. Okay, so this is the original image and this is okay. I'll just do the central pixel so that there is no confusion out there. 201. Okay. So now what when you apply median filter on this, this is original and this is noisy. And the noisy bit is this one. Okay. Now given this, how will you apply median filter on this? On sample.
Arrange the filters, arrange the pixels in ascending order
Hmm.
and find out the median.
Okay, so someone says that I will do it blindly. 1, 1, 1, 1. Okay, and then 2, 2, 2. Okay, how many twos are there? 4,
One more two, yeah.
and then 5 ones, right? Okay, so this is for the first image, and this is for the original one. What about noisy? Starts with 0, 4 ones, 4 twos, right? Oh, 3 twos. Oh, there are 5 ones. Fine. Okay, so now if I apply median filter on noisy image, what does it give me? The central pixel will change to
One.
1. Okay. Here the central pixel will change to?
One.
Okay. Okay, so first let's just go about denoising. So when we denoise this, so it's clearly visible that 1 is closer than 0 from 2, right? So this difference of 2 minus 1 is less, right? 2 minus 0 will be more. So when you actually use a median filter on noisy image, you will feel that you will perceive it in a way that okay, it has been filtered out, the noise has been filtered out. But actually, the point is you do not really. I mean, it's not always possible that you can completely remove the noise out there. So you have just you're trying to compensate for the noise by taking median filter. So you're trying to bring the pixel values closer to the actual value and not exactly to the same value. Fine. But now, if this is some original image, and again I applied median filtering where there is no noise, you can see that the central pixel will be replaced with 1, right? So it is still good enough, you can say. Even if you apply median filter on a uh, yeah, if you apply median filter on an original image, it's still good enough. It will not distort the image too much. It will just distort it to a small extent. That's why median filters can be used to some extent. Where do you think it's not useful?
For a huge pixel data, like for huge images, where the computation, because median filters makes the computation very heavy.
Okay. So nowadays we have so many things. We
Yeah.
have GPUs, right? We can just
Yes.
parallelize it and do it fast.
Yeah.
Okay. Anything more? I mean, that's fine. That's the problem with all kinds of filters, not specific to median. Any specific problem with median filters that you think of, given that I gave you this example? So median filters just replaces the median value, right? Blindly. Yes.
It works on odd
Okay.
matrix.
Our window size is always 3 cross 3 or 5 cross 5, so it
Yes.
will always give us odd uh,
So if we
set of.
have even number of like 1024 by 1024, then we have to go for padding and
No, no, no. So this is the window size. It's a patch on the image. It's not the full image. So you always consider small patches and then you check, right? You don't take the full image as input to the median filter for a specific median filter. So if this is a full image, you take a small patch, for instance, here, and this is the patch which is representing here as noisy patch or whatever I'm representing as original or noisy. You don't apply median on the full image directly. Otherwise, all the values will be same, right? Do you agree with that?
yes,
So if
yes.
I apply, if I take all the values in the image, then it will be a big array out there, and then you'll choose the center one for all the pixels, right? Then it will image will be constant image. There won't be anything left out.
If we use this median filter window lower side on lower side like 3 by 3, then the image is good. But if we increase this window size, then the image becomes more and more blur. We won't get
Yeah,
that good results.
yeah, it becomes like blobs. If to be specific, if I give you some example like this, if you have an edge like this, right? If you have an edge like this, and if you have some median filter which passes at the middle of the edge, right? So it will replace this middle value with some of the nearby values. Yes. So what happens if your edge is very thin, that it just crosses three elements out of the 9 elements? It can just be removed. Very thin edges can be removed completely, even if it's a non-noisy image, right? Because it just does does take median in that window, right? It blindly takes it. It doesn't consider whether you have an edge out there or not, or any other information. It just takes median of a set of numbers and then replaces it with the central pixel. Yes, so whenever the frequency content is high in the image, you might not really want to use median filters because they actually tend to, I will not say they'll reduce the frequency component, but they'll distort the image. Okay, is the intuition clear? Yes, no?
Sir.
Yes, okay, that's good then. So yeah, median filters you would generally not like to use when the frequency content of the image is high. I'm talking about the original image and not the noisy image. Okay, given that, we can just come back to the question and solve it. So since we have this, we can unroll this and write it as what's the minimum value out there for the patch 10 and then 60, 70, 120, after that 130, 141, oh, 126. I left 126 in between. 126, 130, 141, 161, 238. Okay, so you have 9 numbers out there. What is the median value?
126.
Yeah, so this is the median value. So we'll replace the central pixel 10 with 126. That's the answer. Okay. Any doubts? Okay, we'll move on to the next question then. Okay, so we have some. Is this visible? Should be visible down, right? Okay. So the an image enhancement technique that attempts to improve the contrast in an image by stretching the range of the intensity values it contains to span the desired range of values is called what? Okay. So we have 4 options here. I'll just put it. Yeah. What is non-histogram equalization? Has anyone heard of it?
काले हुए तो स्पैगेटी बना दे इसको.
Okay. Anyone knowing about non-histogram equalization?
All pointing operations are spatial operations, you can call.
Yeah. Okay. They are. I mean, whatever that doesn't specifically use histogram. What about non-linear contrast stretching?
The transformation function is non-linear. For example,
That's
gamma
true.
correct.
Yeah, for instance, gamma. What is histogram equalization? Using histograms, whatever transformation we get, the CDF transformations that we discussed earlier. And what is linear contrast? What is linear contrast?
Linear contrast is mapping the histogram to decide histogram. Current image histogram.
Okay, got it. Well, or anyone else? What an idea of linear contrast?
Okay, sorry, linear contrast. Transform function will be linear.
That's correct, but but anything more on that? I mean, that's evidence on the name, yeah.
Yeah,
But
yeah, yeah. Answer by answer.
uh, so if did anyone?
Piecewise.
No, it's not piecewise. It's full, completely full linear contrast. So it's a very simple formula that people generally read in class 7 or 8. So it's like y minus y1 on x minus x2 is equal to what?
Tangent.
Yeah, tangent is some other point y minus y1. So for our specific purpose, what is x2, x1, y1, what is x2, y2? I
It's
can, yeah, yes,
you mean to say x1 y1? It's like a input y, and y2 x2 is a different
yeah. So
space.
y2, x1, x2 is a different space, y1, y2 is a different space. So x1, x2 comes from original image, and y1, y2 comes from the transform. Now, given this, I mean, I'll just keep the variables that we use generally. It's not x and y here. We are dealing with what? Intensity values, right? So for intensity values, we are using R and S. So S minus S1 upon R minus R1 equals to S2 minus S1 upon R2 minus R1. Fine. Given this, we'll take R1 as minimum intensity value in the image. R2 is the maximum intensity value in the image. Fine. It is the original image. And S1 is again minimum intensity value in final image. And S2 is maximum intensity value in final image. Okay. Is everyone clear with this? So if you know the final range in which your intensity should lie, then S1 and S2 denote the minimum and maximum. And in R1 and R2 is just the input intensity value out there. Yes. Given this, we would generally like to do a contrast stretching so that it covers the whole range. So for covering the whole range, this is 0 and this is L minus 1 for covering the whole range. This is the general idea of the linear contrast stretching. So you take minimum as 0 and maximum as L minus 1. So after you transform, your images will have this minimum and maximum intensity value. Okay, so here we are just trying to stretch it. It's not specifically given how you want to stretch the image values. So what linear contrast stretching is a valid answer, yes? Everyone agree?
Yes, sir.
Linear contrast stretching is one of the answers, and non-linear contrast stretching is also one of the answers, if you ask me. Both are correct for the question that's given. Well, the point is you need to have control on the desired range of values. If you have the control over the desired range of values, then it's fine to use nonlinear contrast stretching. For instance, gamma, as we see, if we choose a constant properly, we can always get it to the desired intensity value, the maximum one, but not the minimum one. So, well, this is not always applicable, then I should remove this. But since for linear contrast stretching, if your desirable range S1 and S2 is known, you can always use linear contrast stretching. So this is the final answer. Histogram equalization does not always give us to the desired range, so this is wrong. And non-histogram equalization, of course, that is very generic statement. We don't know whether we can have our output values in the desired range or not. Okay. So is this question clear? Okay. We'll move on to the
Yes.
next one. Okay. This is an interesting question if you ask me. This is the original image patch given like this, and then we have the final. Then we have a filter applying on top of it. So if you apply filters on this, then what should be the output of application of this filter on this image? Hmm? Anyone? How to proceed?
Need to perform convolution.
Uh, it's specifically written here that we need to do a correlation operation and not convolution. Yes. What is the difference between convolution and correlation? Can anyone tell me the formula? Hmm? Convolution.
We have to flip the kernel for the
Yes.
convolution.
Yeah.
Correlation is no need to flip actually.
So if I write it in 1D
So it's
for continuous functions, how does it look? Okay. So y h of x minus y dy. This is convolution and for continuous uh, functions f and the continuous filter out there. H. Yes. Everyone agrees with this formula. What about correlation? Someone said it right, but I want to write it mathematically. G of x will be minus infinity to infinity f of y h of what is this x plus y dy. Okay, so this is the formula for correlation. This is the formula for convolution in for continuous functions. For discrete ones, you replace the integrals with summations. Summation over the range of y here and here. I mean, yeah, yes. And for every specific value of x, you get you have to do this specific operation. So, is what kind of operation is this? Is it spatial or point? Point operation.
Spatial operation. Need to consider the neighbor pixels also.
Yes, it's a spatial operation. And if you ask me about this, what is this operation? The previous question, image enhancement technique. What is this specific operation?
This is also spatial operation.
Why? Does it depend on the neighborhood pixels?
Yes.
How? Once your transformation is defined, it is the same transformation for the whole all pixels, right? It doesn't depend on the intensity values of the other pixels neighborhood pixels, right? This is the transformation. This is the T of. I mean, if you write it properly, this can be equivalently written as this is S is some T of R. Yes, you just take it right side and then push this S1 to the right. So the S is equals to T of R. So once you define transformation here, there's nothing. It's not dependent on neighborhood pixels. Yes, yes, it is depending on the overall image range, which is fine, but it is not depending upon neighborhood pixels. Yes, why? Because R1 and R2 are what? Minimum and maximum intensity values. S1 and S2 are minimum maximum intensity values of the whole image and not the patch. So once this is defined, it is a point operation.
Yes, sir.
Okay. Any doubts with this? So it just takes the intensity input of that particular pixel and then gives the output, right? There is nothing there in between. So it's a point operation. Okay. So coming back to this question, it's a spatial operation, which is fine. So again, now someone said for convolution, you have to flip the, what do you say, filter. This is 1D convolution actually. You will have 2D equivalents given in the class, even for correlation and convolution. So convolution, you have to flip the filter. That's why you take minus y before integrating and then place it at the specific value where you want to check, which is given by x, and then apply this formula. Again, the same thing for correlation. You have to place it at specific value of x, but you don't flip the filter out there. Yes. So given this question now, how to proceed to solve this? Okay. Yeah. So it's a 5 cross 5. So this is our image, specific image where only the center value is 1 and other values are 0. So this makes our life quite simple. This is our image. Okay. Now how will you perform uh, correlation? Yeah, yes. The question asks for correlation, so we'll have to do that. And we have this filter as such. So what will we do? We don't have to flip the filter. We'll use the same filter exactly, right? What is the next step? How to proceed? Anyone?
First, do the padding for image patch
Why do you want to do that?
because it's the correlation filter is sorry, the filter is 3 by 3,
Hmm.
and the filter given is 5 by 5. We have to give it in multiples of 3. Arrange it in
Okay.
multiples of 3.
Okay. So if you don't really want to reduce the image size, you should always pad it. Yes.
Yes, yeah.
So how much padding you want?
So we have to make it 9 by 9.
Why 9 by 9? This is 5 cross 5,
Sorry, 5 by 5. So
and this is 3 cross 3. So what is the how what do we do exactly? If you are able to visualize that, you can easily calculate how many padded rows and columns you want. What is it that you do with the filters? Okay, so maybe should I say, or is anyone willing to say that? Okay, fine. Given this center pixel, given this center of the filter, we want to place the center of the filter on each of the pixels. Yes. So for instance, we start it from here. If we take center like this, the filter would come like this. Agreed?
Yes, sir.
Yeah. So given this specific center and the specific filter, now you have values which don't actually exist in the image. So as you said, we'll add zeros. So for a 3 cross 3 filter, how many rows you append? I mean, you will do one row at the top, one row at the bottom, one column towards the left, and one column towards the right. That's all you need. Yes,
Yes,
agreed?
sir.
yes,
Yeah.
yes.
So effectively, this is what?
We get 7 cross 7.
Yeah, this is a 7 cross 7. This is very critical while implementation. Otherwise, your image sizes will reduce. Because what generally codes do is they just directly place the center pixel here, uh, the center of the filter here instead of this corner, and which tends to reduce the output size. So we should try avoiding that. So to avoid that, of course, we can do zero padding, or we can just flip it, uh, uh, not flip it. What is it called? The circular copy. So you can just copy the things out here on the rightmost column toward the end column, or you can just copy the leftmost column towards the right column. So this is the circular flip. This is direct copying, or you can keep it zero based on the application. So for this specific case, I'm taking it zero. Given this, of course, now what will be the output of this filter placed here?
0.
Yeah, zero, because all values are zero. And what does correlation do? We'll just place each filter value here, right? What is the correlation? So we'll exactly place the same filter values like this. Why? Because it's a correlation. If it's convolution, then how will it be? That we'll see later. Fine. We'll first solve this question. Okay. So given this, we'll place it here. It gives us zero. Next, we'll place it here. It will give a zero. Here gives zero. Again, we'll go through each of this, and then we come here, our specific area. This use the green one. Yeah, we'll come here. Given this, how will our filter be now? Like this, right? Agreed?
Yes, sir.
Yes.
So given this, now we okay, that's fine. So our filter values will be like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? What is the output?
9.
Right.
Our output is now 9. So we process the first row, which is 0. We actually process the first column of the second row as well, which is 0. But then as soon as we come here, we just multiply each of these with the corresponding element and then take the summation. So it turns out to be 9. What about the next window? How will it look? It might look like this, right? Okay, so sorry. Yeah. So we have our center pixel here. How does it place them?
We get 8 as an answer.
Yeah, because this is sorry. This is how it will look in this specific box. So now 8 will come here. This specific 8 will come here. We are shifting by 1. So our answer will turn out to be 8. Yes. And similarly, if you move here, your 7 actually will be here at the point at wherever 1 is there in the image. So it will turn out to be 7. So what about the next one here? How will it look?
It's
Given
6,
like
5,
going like this,
4.
6
Yeah.
by 4 and then
6,
0
5, 4. Right.
and then 0, 3, 2, 1. Yes. Is everyone clear about this operations?
Yes, sir, get it.
Okay. So why do you think you get this? In the sense, you're just
And that is
getting. Sorry.
impulse. We are
It
multiplying with
impulse.
Yeah.
impulse.
Yes. We are actually taking multiplying, or it's not exactly multiplying, but as we see the correlation uh, formula, it's integrating or summing with an impulse. The impulse just gives the same output whatever it takes in. Yes. But that is when what? That's when you use convolution, not correlation. This is correlation. So your things are flipped. Flipped in the sense 9 was here, it was exactly flipped here. 8 was here, it got flipped here. 7 was here, it got flipped here. 6 was here, it got flipped here. You got the idea? So with correlation, things get flipped even when you use impulse as the function. Okay, this is the impulse function, discrete impulse.
Correlation.
Discrete, this is the correlation output. Do you see, right? Things got flipped with correlation. This is the output. Output in the output, uh, the input. I mean, there is no input; it's just impulse. But if you see the filter values, it got flipped out. But what is the case when you do what is convolution? So we'll just do it once again briefly. So with convolution, what is it that you do? Again, we'll take that box. We'll do zero padding and all. It's fine. If I take this as my current query, what what is it that we do? Again, we place the box here. But now, since we are doing what convolution means you have to flip it, right? So flip it along both the x-axis and y-axis, since it's a 2D convolution. Yes, someone was saying something. So the flipped filter will be, everyone agrees? that if I flip this along this axis, 9 will go here, 8 will go here, 7 will go here, 1, 2, 3 will come here. Now if I flip along this axis, the 9 which was here will come here, the 3 which was here which will come here, right? So it will turn out to be like this. Everyone agrees the flipped filter?
Yes, sir.
Yeah, so once you have the flipped filter, then it's pretty straightforward, I guess. You can just place the numbers 9, 8, 7, 6, 5, 4, 3, 2, 1. Now you see 1 is getting multiplied with 1, and your output will then look like 1. It will come 1 here, right? Again, if you shift it here, 2 will come here, which will turn out make it 2. Yes?
2, 3. Yes.
Yes. And then 0, 4, 5, 6, 7, 8, 9. So yeah, this is a very good example if you consider, some of you have read digital signal processing. So given an input as impulse, the filter, this is the filter response. It just copies the filter, whatever there is out there. Yes, this is the filter, right? This part is okay. This part is the filter part. It's exactly the same as the input filter. So just to clarify, I'll write it here that this is coming as convolution output. So when you do convolution with the impulse, you get the same thing. But when you do correlation, you get the flipped answer. Okay. Any doubts? Okay, then we'll move on to the next question, which is okay. We'll see. So identify the operator. What is this operator? I mean, this is a window given to you like the one given previously like this. What is this operator? Anyone? Any answers? Okay, leave these options. First, how does this operator look? Does this look high pass, low pass, what pass, band pass? That would be an easy way to.
High pass.
High pass.
Why high pass? Why specifically high pass?
Center pixel has a maximum.
Well,
Ah, yeah.
yeah, central.
Not. It's not about maximum. It's about center pixel is positive and other pixels are negative, right? It's. I mean, if it's not even the maximum, it's fine. But the point is, center pixel is positive, other pixels are negative. So there's some subtraction operation going on. So if you remember filters, it was given in the class like this. How does a low pass filter look in time domain? Okay, when I write in time domain, the center should be like this. Yeah. How does low pass filter look? This is the space axis, and this is the value I filter. It represents that axis. Anyone? Looks like this, right? Something above zero. All values above zero, either it can be Gaussian or it's a constant like this. All of this consists your All of this consists your low pass filter. Everyone agrees? What are the examples? Average filter. Which one is the average filter here? This one is the average filter. Yes? Average filter has constant filter values, whatever the range of x you take. And if you do it in 2D, even in the range of y, the values are constant, right? Yes? No? Got confused. So what does average filter look like? 1 by 9 of all ones. Yes?
Yes, sir.
So isn't it constant? If you take a single axis, if I take x-axis like this, so this constant represents this constant value, right? 1 by 9.
Yes.
Yes.
Okay, fine. The same thing happens in the y direction again. So its average filter is also a low pass filter. What about Gaussian? Your Gaussian 2D Gaussian will lie like this. So it's like it's having maximum value in the middle, but it has some low values out there based on what sigma you do. Yes. So for an effective Gaussian filter, what should be the filter size? Anyone?
For FFT, FFT,
For an effective Gaussian filter, what should be the filter size?
it should be window size
What is the
or
window
image.
size?
Two, it's equal to image size. 2 power n.
No. So does someone remember the property of Gaussian filter? Or rather, what is the Gaussian function?
It's a
99% of the values lie in what? Can someone mute if it's not, if they're not speaking? Okay. So the 99% of the values lie in what? 99% of the mass. Not 99% of the mass of the Gaussian function. Okay. Lies in what? Lies in 3 sigma value, right? 3 sigma length. Everyone agrees with that. How does Gaussian function look like? F of x is 1 by square root of 2 pi sigma exponent of minus half of x minus mu upon sigma whole square. Everyone agrees with this?
yes,
This is the
yes,
Gaussian function? Yeah, yes.
yes,
So
yeah,
given this, if you have a Gaussian like this, flowing, it is symmetric actually. My diagram is not. So if this is x, this is f of x. So within first standard deviation, that is minus sigma to plus sigma, you have 60, around 67% mass. And within second standard deviation, how much mass is there? Around 97. I don't remember the exact percentage, but they are of this value. Within 3 sigma, 99% of the mass is there. So for practical purpose, when you have this, when you use Gaussian filter, you should try using 3 sigma or at least 2 sigma, not below that. This is, I mean, your whatever 2 sigma will be equivalent to in the number of pixels, your filter size or the window size should be like that. Agreed?
yes, yes.
Yes.
Okay. So this is something of an implementation aspect, but I guess I thought I should share it here. Okay. So given this, okay, Gaussian is also low pass because all filter values are, I should not write magnitude. All filter values are positive.
Positive.
Yeah.
Positive.
Filter values. So okay, this is for low pass. What about high pass? How does high pass look? So a simple example given is uh, identity minus low pass, right? So what is identity? That we exactly saw
Q1 0.
in the previous question. which is this impulse function. Impulse function is called the identity function. As you see, that returns the same value. Identity function. I'm not saying it as identity matrix. It's an identity function. If you remove this remove identity function with the low pass, which is 1 by 9 of ones, what it turns out to be?
1 1 0
Huh?
minus 1
Minus 1 by 9 everywhere. And the central one will be
0
1 minus 1 by 9. Sorry,
8,
1 by 9.
8,
0 by
8 by
9.
9.
Yeah.
8 by 9.
Yeah. So there is 1 by 9, I guess. I'm getting it back. Fine. Minus 1 by 9. This is center one is 8 by 9. Okay. Others are again the same value. Yeah. So what does this mean? Their center value has some positive part and then the other values have negative part. Effectively, what does your filter look like?
Question.
Have the filter like this? Okay. Your filter should be centered. Fine. If you have filter like this, your center will be positive, others will be negative. It can go above, but it should still be negative. Okay. So this is like x and the filter value. Fine. This is for high pass. What about band pass? What does band pass mean? What does band pass mean? Anyone?
It has two cutoff value.
Yeah, so it just allows to pass a specific range of frequencies. It is neither low pass or high pass. It is somewhere in between. Low pass means all low frequencies will pass, but only high frequencies will not pass. High pass means only high frequencies go away. I mean, goes through the filter. Low frequencies are stopped. But band means just a range of frequencies are allowed. So given this idea that of course, center value is always positive, but other values are positive for low pass, other values are negative for high pass. How should be the band pass? So this part is clear, I guess, that your center value will always be positive, even in band pass, because in both the cases they are positive. Yes.
Yes, sir.
Yeah. What about the other values? So should you use all negative or all positive? If you use all negative, again it becomes high pass. If you use all positive, it becomes low pass. But it is band pass, right? It will use some positive and some negative. Yes, to make it
Yes.
Yes.
to
Yes.
cover both the frequencies. Yeah. So given this, it will look like this, something of this sort. It's not an exact function. I'm just drawing it for illustrative purposes. Again, this is x and this is filter value. So what this does is this part helps you to get the low frequency component, and this part helps you to get the high frequency component since you're subtracting these two parts. So in effect, it's like cutting some part of low frequency, some part of high frequency. So it's a band pass. Cutting some low frequency and high frequency parts. Okay, so your band pass filter will have central pixel central value as positive. Maybe these values are negative, but if you take a bigger size 5 cross 5 filter, then you might see positive values again. So this is how the band pass filter would look like. Okay, given this whole idea of filters, we'll come back to the question because ultimately you have to solve the question, right? So given this operator, what is this? Can anyone tell me it's a low pass or high pass? Or is it band pass? Just see the filter. Don't see the options. We'll go through the options. Is it low pass? Sorry, I can't hear that. The two people responded together. I just heard noise. I'll low pass that so that I can uh, filter the noise. Anyways, yeah. So for this
It
question,
is
what is?
band
Sorry,
band band pass.
band. So okay, is it low pass? Yes or no?
No.
No.
No. Okay, yeah, it's not low pass. Is it high pass?
Yes.
Why?
Because the center pixel has a positive value and other values are negative.
Yeah, it's not pixel by the way. It's central
Sorry.
filter. Filter
Yes.
value at the center. Low
Yes, sir.
pass, no. High pass, someone said yes. What about band pass?
No, because it is having all the negatives
Yeah,
except the
zero is
center one.
fine, but it doesn't have a positive value. So it is not band. I mean, it's not having a positive value apart from the center part of the filter. Okay, so it is not band pass. It is high pass. It's clearly seen. Okay, do you know what Laplacian is? Laplacian operator.
It is high pass filter. Laplacian.
It is yeah, a differential filter.
Differential, yeah.
Differential.
Second order.
Yeah, second order derivative. If you take it in, if you are in continuous spaces. So if you just take double differences, that turns out to be Laplacian. So Laplacian is a high pass filter. Okay, that's fine. Gaussian
Low pass filter.
Low
Low
pass.
pass
seems like
filter.
that. All values are positive, so it's a low pass. Fine. What about LOG? Laplacian of Gaussian. So what you're effectively doing is you're first applying Gaussian and then apply Laplacian on top of it. So that's called as Laplacian of Gaussian. Just for reference.
Then low pass.
It will be band pass. LOG.
Okay. Two answers. Which one do you want me to choose? Okay, the low pass person. Why do you say it's low pass?
Because first you are applying Gaussian, correct?
Okay.
Then you
And
get the low frequency only.
low frequency stage and then
Then you are doing differential.
differences. But the high frequency, it
Yeah,
takes
that
out high
is,
frequency from the remaining part.
yes, yes.
So what did Gaussian do? Removed low frequency part. What did Laplacian do?
Laplacian
Remove
detect
high
the edges,
frequency.
sir.
Gaussian. Sorry, I did it wrong. Sorry. What did Gaussian do? Removed high frequency part. It's a low pass, right?
Yes, yes.
So
It
it
removes
removed
a
high.
low pass.
Yeah. So if you have frequencies like this, what Gaussian did is it removed this part, this part. What Laplacian did is it removed low frequency. So what is left with us?
Band
Someone
pass.
pointed out
It's
Yeah, yeah,
band
band
pass.
pass. Yeah, yeah.
it's a band pass filter. Okay, great. What if I change the order? First, if what if I apply Laplacian and then Gaussian? Do you think it
Laplacian,
matches?
then depends upon the cutoff. Then again you get a band pass.
Yeah, it depends upon the cutoff, assuming that the cutoffs are not same. They are
Yeah, again we get a band pass.
Again,
even
it will
better.
be a band pass.
Okay, even better. One final question on Laplacian of Gaussian. Is it uh, a linear filter?
Gaussian is linear filter.
Anyone else? So, okay, is Gaussian linear filter?
Yes, yes.
Okay, is Laplacian linear filter?
Laplacian, is not linear, I guess.
Why?
It's a derivative filter,
Okay.
and if you change the order, you won't get the result, same result, right?
What is the definition of linearity?
Linearity, it has to satisfy the four properties.
Four properties. Okay.
Yeah, so
Let me note
I
it.
mean,
Yeah. Yes. What are the four? I'll write it down.
associative. I mean, the linear means you can even change the order.
What order?
I mean, order of transform. T. Suppose if you apply to Gaussian filter either A and B, you can even apply B and A also. Order you can change.
Well, here we only have one filter, whether that filter is linear or not.
Yeah, that on the associative law and that four law.
Associativity is different. It deals with two things. Linearity is actually uh, linearity means f of ax plus b. There is a function f. You
F of
transform
A
this
into F of X plus B.
plus b, right? This is what you want.
Yeah, yeah.
So what is f here in all these options? They are the filters, right? Agreed?
Yes, sir.
And what is a here?
A is we can consider as a scaling.
Yeah, scaling the input. What is x here?
X is current spatial point.
Just a spatial point?
Yes, the I mean,
Well, x here
yeah,
refers to the full
coordinate,
window.
coordinate.
Full
Yeah,
window. The intensity values at the window.
yeah,
Yes?
Yes.
So if your window is 5 cross 5, you take a 5 cross 5 patch, and the intensity values within that 5 cross 5 patch represents the x. A represents, A is the scaling as someone said, and B is translation. So if I change the input values by this specific A and B, do you think the output values will change like this?
yes.
Yes, right?
If a linear means it has to change.
Yes.
If linear means it's fine, yeah. So okay, I'll take simple example now. We might be out of time soon. 5, 6, 7, 8. Let's do big example. Okay, I'll take 1, 1, 1, 2, 2, 2, 1, 1, 1. This is my image. Okay, and if I apply average filter on top of this, what is average filter? Like one sum everything and divide. Rather, average filter will be 1 by 9 of ones. Yes, and apply it on top of this. What will the answer be for the center pixel? Just add all, right? 2, 4,
12
6,
by 9. 12 by 9.
6 plus 6, 12 by 9.
12 by 9. 12 by
Central
9.
pixel will be 12 by 9. Fine. So now if I scale this, I'm leaving B, but even if you add B, it doesn't matter. Now if I scale this, like if I multiply everything by 2, what will your answer be? It will be 24 by
24
9,
by
right?
9. Yeah.
It will be still here 24 by 9.
Yeah, that's it. So this is all low pass filters are fine with this. What about high pass filters? If I take 8 minus 1 minus 1 minus 1 minus 1 like this, what is it initially?
6 by 6.
What is this? 8 to the 16.
6.
16 minus
6.
4.
Not 6. Yeah, 6.
16 minus 6 is 10.
Totally
10,
12. Yeah.
10 minus 4 is 6.
16 minus
6, right?
yeah 6 by 9. Sorry 6.
6, just 6. I'm not keeping the nomination to have 1 by 9. So if we now multiply by 2, what will be? 12 by 9. Yes. It doesn't matter what filter it is. These all filters are linear. Low pass, high pass, band pass. What you're actually doing is just multiplying these individual elements with the individual elements of the image and then trying to what?
Understood. Yeah.
And then trying to just evaluate the answer. That's it. So all
Yes.
filters are linear here. At least, I mean, whatever we are discussing. I'm not saying that all filters are linear. So Gaussian, Laplacian, LOG, all three are linear filters. Okay. So given this, yeah, this is clear. So given this, Laplacian of Gaussian is also linear because applying two linear filters consecutively is also a linear filter. Yes. Two linear transformations together is also a linear transformation. That's why Laplacian of Gaussian is also a linear filter. HOG is actually not even a filter. If someone has heard of it, it is histogram of oriented gradients. Okay, I don't have space to write here. Just write it down. HOG is gradients. So this is actually used when you want to extract features from the image. Features in the sense if you want to extract some special points on the image which will try to capture the structure out there of the image. So that's where HOG is used. It's not a filter. So this is not even a filter, so it doesn't qualify for this question. It's just given to confuse. LOG is linear, Gaussian is linear, low pass. LOG is band pass, by the way. Yeah, and Laplacian is high pass. So given this, what is your answer for the question? You already saw this is high pass, right? And this is the only high pass option. Yes.
Right.
Yes.
Well, now if someone asks what about the actual Laplacian values? Yeah, if you discretize Laplacian values, uh, I mean it's not exactly plus minus one if you do, but if you take some specific weights, you can always end up going like this. So it's fine. I mean you don't really need plus minus ones out there in the filter. When you actually work with these signals, you don't use plus minus one, but you use some weighted versions of it to make it more useful for the application. Okay, any doubts with this?
No.
Um, okay, then I guess we can stop here. There are no more doubts about the session.
Sir, I was having a doubt in question number 5 of assignment 5.
Okay, I don't have the current year's assignment actually.
The hard transform coefficients of n equal to 4-point signal.
Okay, okay, okay. So yeah, you just in the previous class we did a hard transform question, right? You can just apply that. We will have a matrix out there. You multiply the matrix with the given vectors, and then that's it. Whatever is the matrix multiplication gives you the output.
Okay.
So you can just check the previous week's question. We did a similar question. I don't know. It's the same question probably. I don't know. But we did a question on hard transform.
Okay, sir.
Okay then. I'll see you guys next week, same time. Thanks for joining. Bye.
Thanks.
Thank you.
Thank you.